Matt and Brad pull a toy train with 2 coaches with a horizontal force of 10 newtons. The mass of the string that joins the coaches together is insignificant. B experiences a maximum frictional force of 0,7 newtons. Sketch a free body diagram indicating all the forces acting on the 3 kilogram coach. Label all the forces clearly. So a free body diagram starts with a dot. Obviously it must have a weight and equal length normal. Then there is clearly an applied force. There's a tension acting backwards. And then there must be a frictional force. Notice they've all been labeled fully. Then, will coach A experience a frictional force of 0,7 newtons? Briefly explain your answer. We can assume this is the same surface. Remember that friction is equal to mu F normal, and since the normal force for A is less than the normal force for B, you're going to land up with a smaller frictional force on A than on B. Calculate the acceleration of the toy train if all friction is neglected. So now we have the simplest system in the whole wide world. It's a 4 kilogram system being pulled by a 10 Newton force. So F is equal to ma, and its 10 is equal to 4 times acceleration, and acceleration is going to be 2,5 meters per second squared, and it's an acceleration which is a vector, and therefore you have to have a direction. A car is traveling eastwards along a straight road at 15 meters per second. The driver sees a tree, has it in the road, but takes 1,1 seconds before applying the brakes. Once applied, the brakes allow him to slow down at that rate. Unfortunately, it's not sufficient, and he crashes into the tree that long after the brakes were applied. So let's calculate the distance before the brakes were applied. He's traveling at a constant velocity, so we don't need equations of motion. S is equal to ut 15 for 1,1 seconds, and therefore he's going to cover 16,5 meters. Calculate the distance covered while the car was decelerating. So now what do we know? We know that we are in an acceleration mode, so we have to use an equation of motion. And what information do we have? We do know that he was going at 15. He does this for 2,95 seconds. We know the acceleration value. It's a slowing down, so it's negative 3,5 and 2,95. And don't forget to square that, and you'll find you get a distance of 29,02 meters. Determine the total distance between the car and the fallen tree from the moment he saw the tree. So those are just going to be these two added together. So the moment he saw the tree was over there. Here's the tree. We know that he's covered 16.5, and he then covered 29,02. So you're just going to add those together and get 45,52 meters. The car hits the tree at a certain speed, and it takes 0,2 seconds to come to a stop. The mass of the car and the driver is given. Calculate the magnitude of the change in momentum that the car experiences. So change in momentum is equal to mv minus mu. So we are going to say that the car is 1,100. His final velocity was 0. He was going at 4,675. And therefore the change in momentum is 5,1. They only want magnitude, so you don't need, 5,142,5 kilogram meters per second, so we don't need a direction. Calculate the resultant force during the collision. So F is equal to change in momentum divided by change in time, which is going to be 5,142,5 divided by 0,2 seconds, and I then get, and now I do need a direction because they haven't said magnitude, so it's 25,712,5 newtons, and it is the force on the car, so on the car is onto the car. They don't say whether we're going left or right, so that's the best that you can give for a direction. Luckily, the driver is not injured in the collision. He's wearing his seatbelt and the car crashes into a tree. The airbags are deployed. Using the laws of physics, explain how airbags help to reduce the chance of injury in collisions. They didn't ask you to tell me about seatbelts, so don't. Just tell me about airbags. What do airbags do? Airbags slow down motion after collision. That's what they actually do. You still end up hitting the dashboard, but you just do it over a longer period of time. Longer time. You have exactly the same change in momentum, but because the time is longer, okay, longer time, therefore less force. Now we've got the car as a write-off and it has to be loaded onto a flatbed track. There it is. The table gives me frictional force between the tires and the flatbed platform when the normal force is adjusted by adjusting the angle on the flatbed platform. Use the information. First you have to plot a graph. And the graph says show how the changing normal force affects the frictional force. And they very clearly say frictional force versus normal force. It's change in y over change in x. So you must put those into the thing. It says don't cut the axes, so don't go for 0. So this would be your frictional force, and it's in newtons, and this is your normal force, and it is also in newtons. We start at 0, and then you give me nice even, you don't jump halfway through. Let's say 2,000, 4,000, 6,000, 8,000, 10,000, and up here again 2, 4, 6, 8, 10, and you make sure that those are even hops. And when you plot those points, you find that they come to be a little straight line. It asks you not to cut the axes. And then it says graph to show, you have to give a heading, frictional force versus normal force. Please don't use the abbreviations, use long words. Now it says calculate the value of the gradient of this graph. Gradient is equal to change in y over change in x, and that is going to be equal to, I happen to have chosen the following 2 points. And that is equal to 0,87. Now, many of you landed up getting 1. I gave you a margin of error, but try and be a little bit more accurate. What is the physical property that the gradient represents? Well, let's go. Gradient is equal to change in y over change in x. Now, if I rearrange that, we find that the frictional force is equal to the gradient times the normal force. Well, we know another equation that looks a little bit like that. And therefore, the gradient is the coefficient of static friction. And you need to say static because this whole thing was standing still at the time. Draw a fully labeled free body diagram to show the forces acting on the car while it is being held on the platform at that angle. Show the angle, but it's not necessary to include the values of the forces. So now what we're going to do is we're going to have our classic body on a slope. So I put the free body there. I write over here gravitational force or weight. I do not put the components of weight onto a free body diagram. I do know that there is an applied force up because there was a winch holding this up the slope, and there is a normal force. And there is a frictional force, and at this stage you don't really know what the friction acts against the motion, but you don't know whether the applied force is winning the motion or the gravitational force is winning the motion. So I would have accepted a frictional force in either direction, either up the slope or down the slope. Then it says, given that the weight of the car is whatever, oh, and we had to show the 42 degrees, sorry, the 42 degrees is in over there. So this translates into a diagram that looks like this. I've been given a weight, it's 9,800, and I am able to do 2 components, and it's at 90 degrees to one another over there. This component is going to be the component parallel to the slope. This component that's 42 degrees. This component will be perpendicular to the slope. And I'm then able to say that based on that angle, this is my opposite, this is my hypotenuse, and that is my adjacent. So if I'm trying to find the component, magnitude of the component of the car's weight that acts parallel to the slope when the platform is at 42 degrees. So I am going to simply say sine of 42 degrees is equal to the parallel component divided by 9,800, and my parallel component turns out to be equal to 6557,48. Now that is acting down the slope. So it is in this direction over here, downwards. And we've got an applied force upwards. So if we now are asked to find, using the component and the fact that the frictional force is given, calculate the force that the winch has to exert on the car to keep it stationary on the platform. So what I can see quite clearly is friction is less than that weight. So the weight is coming down the slope, and therefore the friction must be acting against that weight. So you're going to subtract it, and it turns out that the frictional force and the applied force really are in the same direction. But as I said, you didn't know it at the time that you did that. And so you land up with 6336,1 and 6557,48, and you do a subtraction and you get 221,4 newtons up the slope. At the scrapyard, a large crane with an electromagnet is used to lift the car off the back of the truck so that it can be placed on the scrap heap. Assume that air friction is negligible. At a particular height, x, above the ground, the net work that has been done on the car is given, and it has gained that much potential energy. Remember, the weight of the car was 9,800 newtons. Using the work energy theorem. When they say you're using the work energy theorem, you have no choice. You need to use the work energy theorem. Well, what is the work energy theorem? It says that the work done, net work done, is equal to the change in kinetic energy of an object. So the first thing that I'm going to do is I'm going to say, how much kinetic energy did it have to start with, and how much did it have to end with? Well, initially it had 0. So change in kinetic energy is equal to final kinetic energy minus initial kinetic energy. And initial kinetic energy was 0. So that's easy enough. And now it's half the mass times the velocity squared. You know the net work done is 250 joules. Let's work out the mass of this particular object. We know that it has a weight of 9,800, which means that its mass is going to be equal to 1,000 kilograms. I take that 1,000 up over there, rearrange, and I find the velocity turns out to be 0.71 meters per second. Calculate the work done by the crane on the car to lift it to that height. Well, there are two things. There's the net work done in terms of kinetic energy, and it has gained potential energy. So the total work is going to be equal to the potential energy gained plus the kinetic energy gained, and that is equal to 10250 joules.